Hi guys, welcome to week 2. So week 2 we're going to learn about electronic configurations and periodic trend. Let's look at the learning outcomes. The first one is to understand and be able to explain principal quantum number, subshell, and orbitals in an atom. Able to express electron configurations of atoms in the form of electron spin notation and SPDF notation. Able to evaluate the relative values of ionization energies in terms of stabilities of different subshell electron configurations. Now all this terminology, we're going to introduce it one by one later in the summary video. First one is, what is that principal quantum number? Now we know that electrons of an atom are arranged in a series of electron shell and that possess certain amount of energy, right? Quanta. We learned that in week 1. What is that quanta or quantum? So it's actually a definite amount of energy that an electrons possess, and they are within a region called electron shell. So the first shells from the nucleus is always the one with the lowest energy, and the second shell followed by the third shell. When they're moving further away from the nucleus, the energy value of an electrons or the energy value of the electron shell is expected to increase. Okay, like shown in the diagram here, as we can see, n equals to 1, that is actually indicates the first shell from the nucleus, and the smaller the number of principal quantum number, the lower the energy. So therefore we put n equals to 1, and then n equals to 2 should be higher in terms of energy for the electrons within that, and then n equals to 3 and followed by n equals to 4. Of course we have further n equals to 5, 6, 7, 8. Alright, so this is what we call a principal quantum number that define the energy value of an electron shell or the energy value of an electrons in a particular shell. Okay, so now look at this. What is that subshells then? Now we learned about electron shells, first shell, second shell, third shell, right? But if you put it under a microscope or a specific instruments to look at the line spectrum, still remember hydrogen line spectrums that will give us some lines here, some colored line, and then they're getting closer to each other, and then you get a continuum, right? So this is a line spectrum for hydrogens. Now each line here in the line spectrums, all these line represents what? Represent a transition of electrons from higher energy level to lower energy level. So let's say, for example, I have how many lines here? The physical line 1, 2, 3, 4, including the continuum will be 5. So 5 line, basically we have 5 different transition of electrons from different level to back to the original state, right? But when you put these things under a specific instruments and you enlarge it, we will find out that each of this line is actually split into doublet and triplet. Just like what I show you here in the diagram, when you look at lines, it tends to show you a sub-lines. So that indicates each electron shell is actually subdivided into subshells. Okay, look at that. N equals to 1 is the first shell from the nucleus. And how many subshell it has? 1. So n equals to 1, you only have one subshell. It doesn't split, right? Basically, it doesn't split. And n equals to 2 is actually split into 2 subshells that label as 2p and 2s. So we talk about that later. And n equals to 3, the third shell from the nucleus, is actually split into 3 subshells, and followed by n equals to 4 is split into 4, and n equals to 5 is split into 5. So what we learned last time were each electron shell is just one shell, and you put all the electrons in, right? Let's say, for example, we learned that for sodium is 2.8.1, and then you have 3 shells then, because I have 3 numbers here. The first shell I should have 2 electrons, second shell I put in 8 electrons, and third shell I put in 1 electrons. And last time some of you used to ask this, how come first shells I only can put in 2 electrons, but then in the second shell I can put in 8, 4 times higher, and then the third shell, in fact you can reach up to 18 electrons. How is that possible? But last time we used to learn that yes, this is the capacity. First shell you only can put in 2, second shell you only can put in 8 electrons. Alright, but now we actually learn that first shell can put in 2 electrons because first shell can only give you 1 subshell. But then when you come to the second shell, it can give you 2 subshell. So you have more space in a way. Therefore, we can put in 8 electrons. And why 8? We'll talk about it in a while, right? So always remember, each electron shell except the first shell, they always split into a subshells. And according to the principal quantum number, the number of subshell is the same as the principal quantum number. All right. So next, how do we define each subshell? We can define principal shell, right? The principal quantum number. The first shell is equals to 1. The second shell equals to 2. And that also indicates the energy level. The greater the number, the greater the energy. But how do we actually define subshells? Now look at that. Subshell, we call that as orbital. It is a region, a space, that has greater than 90% probability of finding an electrons, which means electrons within an orbitals, they have no fixed positions. They are free to move around, but then they can't move out of the fixed region, out of the orbital. So each subshell here, we call that as orbitals, and each subshell is also defined by the following quantum number. So the first one is angular quantum number. Now what is that? Angular quantum number is actually to define the shape of each orbital, the shape of each region or space. Okay, and we have a total of 4 shapes. Usually they put it at 0, 1, 2, 3. Again, just like principal quantum number, they use number to represent different shape. But then later they develop into a state where instead of using 0, 1, 2, 3, I mean, rather than the same as the principal quantum number, that will be confusing, right? So they put it into S, P, D, F. All right, they put it into letter SPDF to represent 4 different shapes or 4 different angular quantum number. So the first one is to define the shape of the subshell or the orbital. The second quantum number we know as magnetic quantum number. Now, magnetic quantum number is to define each shape will have different orientation. Okay, let's say I have a circle, that's one shape, and then I have a dumbbell shape, which I'm going to introduce later. This is actually the S orbital, which has a circle, a spherical shape, and this is actually P orbitals. Now, of course, if you look at the S orbital or the S angular number, within this spherical shape, we don't have any orientations because it's spherical. That's only one orientations. But then if you look at P, right, we can actually put this dumbbell shape into different orientations. Now, what are the different orientations here? It's something like that. You have our axis, right? Y-axis, X-axis, and then we have Z-axis. Make sense? So these P orbitals, also called the P quantum number, they can actually lie on these X-axis, or they can lie on the Y-axis, or they can actually lie on the X-axis. You see that? They all having the same shape, same quantum number, angular quantum number, but different magnetic quantum number. This is to define the orientation. Okay, how they oriented along the axis, X, Y, and Z. So for P, you have different orientations, 3 different orientations, right? So that's magnetic quantum number. And what about spin quantum number? Spin quantum number is actually the position of an electrons within an orbital. Like I said just now, an electron has no fixed position in the orbital because it's just a space where you have 90% to find an electron. These free electrons are free to move within that region, within that space, right? And then, even though they have no fixed position, each electron will have its own spin state. What is that spin state? Spin state is when I have an electrons. Let's say this arrow is 1 electrons, and these electrons are free to spin, either clockwise or anti-clockwise. So they can spin in either directions. And knowing that this is actually negatively charged because it's an electrons, right? So when a charged particles are actually spinning in one directions, that will make them a small magnet. Okay, that will change them into a small magnet. And this magnet, when they're spinning in one directions, they create a dipole moment, like a magnetic field, right? So when you put 2 electrons together, that's spinning at the same direction. If they're pointing upwards, meaning that you're spinning clockwise. So they're spinning like that. Same thing for this, they're spinning at that. Now, when you put two electrons spinning at the same direction together, what will happen? Because both are actually a small little magnet, right? Because they're spinning in the same directions. So these small little magnets, when you put them together, they tend to repel. So this will create a repulsion between electrons. And this will make that particular orbital with these two electrons become unstable. It will make them unstable because the electrons in it are keep repelling each other. They keep repelling and they keep moving away from each other. That will make them unstable. And how can we solve these problems when you put two or more electrons into a same region or a same space? So we do that by putting them in opposite directions or opposite spinning directions. Let's say if you put an electrons, if an electrons in a region is pointing this way, another electron then next to it should be in opposite directions. So pointing upwards is clockwise, pointing downwards it's anti-clockwise. It's the inverse of that. So when you put two different directions or two different spin state electrons together, that will actually minimize repulsions. All right, so because they're spinning in different directions, instead of repelling, they might actually attract each other, just like a magnet. North pole, they actually repel. North pole and south pole, they actually attract. So when you put electrons, more than two electrons or two electrons into a similar space or similar region called orbitals, then you have to put them in different spin state. And this is what we call spin quantum number. And this spin quantum number is actually either positive half or negative half. Again, what is that positive half, negative half? Positive half is clockwise, negative half is anti-clockwise. This is for your understanding. All right, so they use this to represent or to define the spin state of an electron. So it's either positive half or a negative half. And when you put two electrons together, again, it has to be one positive, one negative. Makes sense? Because they try to minimize repulsions. So these are the quantum number to define the subshells. So in total, guys, how many quantum numbers that we learned? Number one, principal quantum number is to define the energy level of the electrons within a space, within a shell. All right. Next, we look at angular quantum number. This is the second one. Angular is to define the shape of a specific subshell, orbital. And then the third one is magnetic quantum number. A specific shape of a subshell can be in different orientations, depends on the shape and whether they can be oriented. And then number four, we look at spin quantum number. Within an orbital, the electrons in it always in opposite spin state, always spinning in opposite direction to minimize repulsions. So these are the four quantum numbers that we learn. And this will be the shape of S and P orbitals. Like I said just now, S orbital or S subshell, all right? S subshell is actually having a spherical shape. So therefore, there's no different orientation. There's just one orientation for it. And then for P orbitals, you have Px, P1, and Pz because they can orient themselves at different axes. If it is on the x-axis, then it is 2px. 2py will be in y-axis, 2pz will be on z-axis. So this is how they arrange orientation. See that? And then for d orbitals, it's even more complicated. They have dxy, means these orbitals is actually oriented between y and z-axis. dxz, dyz. Okay, d square, y square is actually on x and y axis together, and then dz square is actually on the z-axis only. So these are the symbol for you guys to notify, to realize that, okay, this is how the orbitals arrange. And you see that the d orbitals here is slightly different from p orbitals. P orbitals is just single dumbbell, single infinity sign, right? And for d orbitals, they actually double. Two dumbbell together consider one orbital, and you have 5 of them. So these p orbitals have 3 different shapes. Not shapes, sorry, 3 different orientation. Therefore, it has 3 magnetic quantum number because this is defined orientations. And for d orbitals, it has how many different orientation? 1, 2, 3, 4, 5. So you have 5 orientation, meaning that d orbital has 5 different magnetic quantum number. Okay? Right? So f orbitals, even more. Look at that. It's even more complicated. You have different shapes now. F orbitals is itself is one particular shape, a specific shape, and this specific shape can be arranged in how many different orientations? 1, 2, 3, 4, 5, 6, 7. 7 different shapes. So you have 7 magnetic quantum number. You see that? So this is f orbitals. Now I'm just showing the shape. What you need to know at this level, you just need to recognize the shape for S and P. D and F, no, you don't need to yet. All right. So this is just to show you a particular shape, which is particular angular quantum number, and then each particular shape will have different orientations. Therefore, we have D, you have 5, F orbitals, you have 7, P orbitals, you have 3, S orbital, you only have 1, which is a spherical shape. That's it. Okay. And before I move on to the next, right, each orientation here can actually put in 2 electrons. Always remember that. Each orientations can fit in 2 electrons. Let me show you this summary. See, shell number, this is principal quantum number. So shell number 1, how many subshell it has? 1 subshell, like we learned that, right? And then this subshell is actually named as 1s, 1s orbital. Okay, subshell and orbital is the same thing, 1 orbital. See that? So number of orbitals in the subshell, of course, is just 1, and then maximum number of electrons in the subshell is 2. Why? Because s orbital is actually having how many orientations? Only 1 orientation, right? Because it's a spherical shape. So 1 orientation meaning that you can put in maximum 2 electrons. And what if you have second shells? Yeah, second shell, I should have 2 subshell, which is 2s and 2p. Okay, now your turn. 2s is s orbital. How many orientation for s orbital? 1, because it's spherical. So this one can fit in 2 electrons. Done, finish. You can't put in more. What about p orbitals? P orbitals can be x, y, and z. 3 different orientation. So if you have 3 orientation for the p orbitals, meaning that how many electrons you can put in? Maximum. Each orientation is 2 electrons. You have 3 now. So maximum you have 6 electrons. So I can put in 6 electrons. So altogether, guys, when you add them up in second shell, how many electrons in the second shell? Therefore is 8. Still remember, second shell we can put in maximum of 8 electrons. Why? Because it has a subshell, and these 2 subshell is actually 2s and 2p. 2 electrons in 2s, 6 electrons in 2p. There you go. So that's why it is 8. And let's look at the third one. If I have a principal quantum number 3, this is the third shell from the nucleus. And because it's 3, therefore I should have 3 subshells. And these 3 subshells will be 3s, 3p, and 3d. Again, let's try. 3s, again, s orbital. The 3 is just to indicate that it is from the third shell, nothing much. And s, how many electrons you can put in s orbital? Because you only have 1 orientation, so 2 electrons max. What about p? Just now we did that, 6 electron maximum. And d, let's go back to d orbitals just now. D orbitals, how many orientation? 5. So 5, you have how many maximum electrons you can put in? 1 orientation, 2. So 5 mean you can put in 10 electrons. Come back here. So I have 10 electrons. So total up 6 plus 10 plus 6 plus 2. Total, how many electrons you can put in into the third shell? N equals to 3. Total of 18 electrons. Okay, now that's the reason why different number of electrons fit into different shells, different principal quantum number. First quantum number, first shell is always 2 electron maximum. Second shell, 8 electron maximum. Third shell, 18 electrons maximum. You can't put in 19 electrons in the third shell. If you have the 19 electrons, then these will go into the fourth shell. You see that? So this is how we arrange. We put in the electron. Let's say I give an element of 20 electrons. How can you put the 20 electrons into the shell? So you know that the first shell is putting in 2 electrons, then you just put in 2 electrons in the first shell, and then 8 electrons in the second shell, 18 electrons in the third shell, like that. You just put it in. Okay, it sounds easy, but then since we know that when we put more than 2 electrons in a shell or in a subshell or in an orbital, we need to follow the spin state. Still remember? the two electrons or more, when you put them together into the same region or same shell or same orbital, we need to minimize the repulsion. So they have to be in different orientation. Alternately, one is pointing up like that, like one up, one down, one up, one down, one up, one down, like that. They will try to do that. So there are some specific rules that we have to follow in order to arrange the electrons in different shell and different subshells or orbital. All right. Now that's the first rule, Aufbau principle. What is that Aufbau principle? This rule actually states that we have to fill up electrons from the shell with the lowest energy. Does that make sense? So we always fill up electrons from the first shell. We always fill up electron from n equals to 1. Once you fill up n equals to 1 full, then you move on to n equals to 2. And n equals to 2 has how many subshell? 2s and 2p. Once these two are full, then you move on to n equals to 3. And 3 you can put in how many? 3 subshells and go on. And one thing good is this Aufbau principle actually give you the sequence. You see that? So this following the sequence, first we go for 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Just follow the sequence here by putting the recommended number of electrons. Just following this sequence. Let me give you an example. I need to erase that first. Okay, so an example will be something like sodium, right? Now we learned that it has 11 electrons or protons, right? Same thing. So what is the configurations that we used to learn, that we're used to familiar with? It's always 2.8.1, right? 11. That's right, 2 plus 8 plus 1. But if I want you to convert it into this so-called SPDF notation, SPDF notation, this is a way to show electronic configurations in terms of SPDF, in terms of different shape of an orbital, right? Different orientations. So let's do this. Now, if follow Aufbau principle, first one started out with 1s. And s orbital, guys, how many electrons you can put in? S orbitals, you only have one orientation, therefore 2 electrons. All right. Next, after 1s is 2s. So 2s. How many electrons you can put in 2s? Same thing. It's still s orbital, 2 electron maximum. All right. And then next, after 2s is 2p and 3s. 2p and 3s. So let's put it in and see whether we have enough space to put in all 11 electrons. So p orbitals, how many electrons we can put in? 3 orientation, right? X, Y, Z. So each orientation is 2, therefore 6. So now I have put in how many in total? 10. And I need only 11. So one more electron. Next one is 3s. 3s orbital, you can put it a maximum of 2, but now I only left 1. So yeah, just put in 3s1. You don't have to actually fill it up. All right. I mean that's the remaining electrons. So we just speed it up like that. So this is the electronic configurations in SPDF notation for sodium. There you go. So this is how you write an SPDF notation for sodium atom. All right. Let's give you another example. Let's say I have chlorine, right? So I guess I will erase that. So for chlorine is supposed to be 17 electrons, and the usual configuration is 2, 8, 7. And you may try together with me. Start up with 1s, 2, 2s, 2. Follow the sequence, 3s, 2. Sorry. It shouldn't be 3s. It's 2p, 6, 10 now. My bad. 10 now. And then I have 10. I need 17, right? So continue. 3s. I put in 2. And then 3p. Okay, there you go. Now, I have 6 plus 4, 10, 10 plus 2, 12. I need another 5. P orbitals, you can put in a maximum of 6. I have 5 remaining. Just put in 5 then. So this is the configurations. Let me erase this in case you guys are, yeah. You see that? So I'm going to compare it again. See, 2 is the first shell. So first shell, I have 2 electrons. Makes sense. Second shell, I have 8 electrons. This is second shell, right? Under 2. So second shell I have 8 electrons. Third shell I have 7 electrons. Do we have that? Third shell means the third quantum number. Yes, 5 plus 2, 7. See that? So exactly the same thing. 287. Nothing wrong with 287. It's just that we are giving them a more detailed, more specific arrangement in terms of SPDF. So they know how each electron's located in each particular shape of orbital, particular orientations of an orbital. This is how we make use of Auber principle. Okay, I hope this helped, but of course, just let me know if you need any help, of course, in the tutorial. Okay, next, Pauli exclusion principle. This is the second rule we have to follow. Now, I have explained that. In fact, when you put 2 electrons or more into an orbital, you have to put them into opposite direction. Just imagine that I have one s. S orbital can put in how many electrons, guys? 2 electrons, right? Now, just imagine I have a box. Each box you can put in a maximum of 2 electrons. So 2s has 1 box. What about 2s? I mean, s orbital has 1 box because you only can put in 2 electrons. 2s also 1 box because s orbital I can put in 2 electrons. 2, 2. What about 2p, guys? How many electrons again I can put in the 2p? 2 plus 2 plus 2, right? 3 different orientation, 6 electrons. And if it is 6 electrons, so how many boxes do we need? 1 box, 2 electron. So 6 electron means you need 3 boxes. Or you can do it this way. The number of orientation, the magnetic quantum number, if you have 3 different orientation, meaning that you will need 3 boxes. Okay? Let's say another example, d orbitals, 3D. So ask yourself, d orbitals, how many orientations do we have? Let's go backwards. D orbitals, I have 5 orientations. 5 orientation meaning that I will have 5 boxes. So 5 boxes. Prepare for yourself 5 boxes. 1, 2, 3, 4. 5 boxes. Alright? So each box you can put in 2 electrons. And how do we actually put in the electrons? We put in the electrons in pair, and they should be in opposite spin state. So when you put in electrons up, the other one should be down. Up, down. Let's say through 2p4. So again, you put in up, down, up, down, up, down. So make sure 2 electrons into each orbitals. Sorry, maximum 6, right? You can put in electrons into 1, 2, 3, 4, 5, 6, like that. So this is how you put in electrons. It has to be in opposite spin state. This is so-called Pauli exclusion principle. All right? And next one is Hund's rule of maximum multiplicity. So this is when, if you read the definition, is something like that. In a set of orbitals of equivalent energy, electrons tend to occupy the orbital singly first. This is the key. Occupy singly first before pairing. So, what does that mean by a set of orbitals with equivalent energy? Let's say 2p. All right? P orbitals, how many boxes? 6 electron, 3 different orientation. I have 3 boxes. And then I have 2p4. Let's say only 4 electrons, not 6. I only have 4 electrons left, and I'm going to put it in here. How can you put in? You always put up singly first. 1, 2, 3. Make sure you put in single electrons in each boxes with the same orientation. Now, you may ask, why don't they repel each other? No, they won't, because now they are in different boxes. Make sense? They are in different orientation, although they are within the same p orbitals, same shape, but different orientation. So they will not repel each other even though you put them like that. But then, when next, you're going to pair them up, right? I have 1, 2, 3. One more to go. When you pair up the 4th one here, then you have to put it as opposite directions. So we always fill up singly first before we pair them up. This is what they meant by maximum multiplicity. This is under Hund's rule. Hope you can get that, right? So these are the 3 main rules that we need to follow. And I've shown you what is that SPDF notation, spectroscopic or SPDF notation. The same thing, guys. So this is how you write for sodium, right? And another way of presenting electronic configurations in terms of SPDF will be in the orbital box notation, which what we learn here, right? So different orbitals will have different orientations, and different orientations will have different number of boxes. So the same thing basically, 1s2, you represent it by a box. 2s2, represented by the box. 2p6, I have 3 boxes, represented by 3 boxes. And 3s1, represented by 1 single box, because s orbital. And each box in it should have a pair of electrons, if it is, if any, and these pair of electrons should have different spin state. So this is how we write in box notation, or you can write in the form of energy axis, energy increasing. 1s, obviously 1 is closest to the nucleus, so this is the one with the lowest energy, and then followed by 2s, 2p, 3s, and this is actually following the Aufbau principle as just now. Okay, because we'll always fill up the lowest energy first, and then followed by higher, higher, and higher. That's how they came up with Aufbau principle. This is according to energy level. All right, so these are the 3 rules and how you draw it. So far, I guess everything is on track. Next, in chemistry, right, we always have some exceptional cases. You know, one theory or one rule doesn't apply for all. They always have some exceptional case, and these will be one of them. Look at that. If according to Aufbau principle, sorry guys, I'm going to jump back to the Aufbau principle page, where I'm going to show you the energy level of 4s and 3d. Okay, if you can see that, following the energy level, first I started 1s, 2s, 2p, 3s, 3p, and then 4s, then only 3d. Can you see that? In terms of energy, right, we always start from 1s to 2s, and then 2s to 2p, 2p to 3s, 3s to 3p, 3p not to 3d, but interestingly it is 4s. Then only it turned into 3d. Why? Why not 3p, 3d, and then 4s? Why is it in an opposite way? Okay, they arrange in a strange manner, right? It's a bit weird. They go to 4s first, then 3d. Now, a simple way to explain that is this. This arrangement from 1s all the way until 3d in terms of energy, of course, this is the lowest, and this is the highest so far. I mean, of course, after that, you still have some more. So until now, amount until 3d. 3d is still the highest so far, right? So they arrange in an energy level. Obviously, Aufbau principle, like I said, they base on energy level to arrange them. So in this case, we can see 4s is having lower energy than 3d. 4s orbital is having lower energy than 3d, and that's why they arrange in such a way. 4s first and then 3d. And you may ask, why? Why 4s is actually lower energy than 3d? So this one, we have to go back to another diagram just now, which is, sorry for jumping around, this one. Now, if you can see that, if you realize it just now, maybe it's too fast. I skipped the slide. Look at that. This is all the subshells, right? And in terms of energy level. So can you see that? 4, n equals to 4, the fourth shell, the principal quantum number, the fourth shell split into 4 subshell, right? The first subshell that splits out is 4s. And this 4s, you see that? It's actually overlapped with the 3d. It appears that the 3d is actually higher than the 4s in terms of energy. See that? 4s and 3d is a bit awkward here, is they overlap in terms of energy. 4s appeared to be lower energy and 3d appeared to be higher in form of energy. And the simplest way to explain that is 4s. Alright, 4s. S orbital, how many boxes? 1. But 3d, you have 5 different orientations. So altogether, you have 5 boxes. And these are the orbitals that without electron yet. So in this case, in a simple way to look at it, which one is more stable? The one with 1 empty box or the one with 5 empty boxes? Obviously, the one with 1 box is more stable because the max you can put in 2 electrons. No matter how they repel the 2 electrons, even though they are in a different spin state, how unstable can it be, right? But for 3D, imagine I put in 10 electrons. See that? 1, 1, 2, 3, 4, 5. I put in simply first according to Hans rule. 5, 6, 7, 8, 9, 10. Then only I pair them up. Imagine how many pairs of it. Even though they are in different spin state, there will still be some repulsions, and you have 10 of them, and you have 5 pairs of them, and these will actually contribute a lot more repulsion than 4s, and therefore they are unstable. When they are unstable, meaning that we can judge it based on energy. Something unstable meaning that they have high energy content. This is always true. All right, so this is why we 4s and 3ds be awkward in terms of energy level, and that's why they arrange in such a way. 4s first. All right, now come back to this. Okay, now before they fill up electron, yes, 4s is lower energy, 3d is higher, right? But once 3d fill up with electrons, see that 1, 2, 3, 4, when they start filling up electrons, the energy level interestingly flip. So the energy of 3d, once you fill up electrons, they tend to drop even lower than 4s. Now they're back to the arrangement, which is makes sense. They're going downwards. You see that? So 4s now is actually higher, and this is actually lower in the energy. Now this only happen when the 3d start filling up with electrons, even 1 electrons. Okay, so because the presence of electrons actually in a way stabilize it, so they swap. So what you need to know here is whenever you involve 3d, then the sequence will be off. But then one thing important is when you fill up electrons, we always fill up 4s first. That's the rule of thumb. Yes, we always fill up 4s first because 4s is lower initially. But once we fill up 4s, let's say 4s 3d, and then right? I still have 5 electrons remaining, so I try to put it into 4s and 3d. Fill up which one first? Obviously 4s first, because 4s is having lower energy now. So it's inner, it's closer to the nucleus. 3d is further. So I fill up 4s too. And then how many more left? I have 5. 5 minus 2, I have 3 electrons left. And these 3 electrons, I have no choice but to put in the 3d. Now I actually put electrons in the 3d, right? So it's supposed to be 3d 3. Once you fill up 3d with 1 even in single electrons, they swap place. So now they're no longer arranged in such a way. The energy level of 3d now is lower, 4s is higher. So now 4s is the outer orbital, the one that on outside, the one that further away from the nucleus compared to before. So this is how we write the electron configuration. So this is an example given. See that? We don't write in this way, 3d1 4s. Sorry, we write in this way, 3d1 4s2, but not 4s2 3d1. This is wrong. Should be in this way. But then, which one we fill it up? We fill up 4s first. Don't forget. You just swap the place. Okay, so I hope you can get. Maybe I give you another example, right? I give you another example. Let's say I have an element X with 23 electrons. Let's say element X unknown, but I have 23 electrons. So how can you fit it up according to Alpha principle? Let's start with this: 1s, 2, 2s, 2, 2p because it's 6, right? Maximum. I still have a lot. I have 23. So 3s2, 3p6, 4s2. Always remember up to 4s2. I fill up 4s first, huh, guys. Here is giving us 20 electrons already. So 23 minus 20, you get 3 electrons left. And these 3 electrons, I have no choice but to put in 3d3, right? But is this the correct way of writing? Since you involve 3d, you have to swap the place. So now you should write it as here all the same, and then continue 3d3 4s2. That's how you write it. So once you fill them up, then only you swap the place. We don't swap it and then we fill up, because if you swap it first, you will fill up 3d first. That is wrong. We always fill up 4s first, then only 3d, and then we rewrite it because now the arrangement changed. Is everybody good? Right? So this is how it looks like. And next one is another 2 exceptional cases. And how do we explain in terms of chromium and copper is something like that. Look, when we have p orbitals where I have 3 boxes. D orbitals should have for 5 orientations, I have 5 boxes, right? Okay, this is how it looks like for the one that more than 1 boxes. P orbitals have 3, D orbitals has 5. Now, there's a rule here. When you half filled, or fully filled, p or d orbitals, that will actually enhance the stability. Let's say, for example, I have p3, 1, 2, 3, right? p3. Simply first, hunt through. Compared to p4, which one is actually more stable? This one is more stable because it's half filled. Okay, this is more stable because it's half filled. And then let's compare. I have d orbitals and then I have 1, 2, 3, 4, right? d5 compared to 1, 2, 3, 4, d7, let's say. So which one is actually more stable? d5 because it's half filled. Okay, now what if I have full fill? Yes, again, full fill also the same. The same case applies to if you have full fill. Let's say I have p6. 1, 2, 3, 4, 5, 6, right? Compared to p5. 3, 4, and 5. 1 unpaired. So which one is more stable? This is more stable. And why are we learning this? Why do we need to know which arrangement, which number of electrons in the orbitals are more stable? Because this thing is going to be associated with its ionization energy. Now, let's take this opportunity to explain what is that ionization energy again. Ionization energy, let's see how long is that now, 41 minutes. Okay, I'll try to finish it as soon. What is ionization energy? Ionization energy is the energy required to remove an electron, right? So, if you're removing an electron from a more stable configuration, which is p6, or when you remove an electron from p5, which one do you think you need more energy to remove it? You get what I mean? So now I'm trying to remove 1 electron from p6 compared with I'm trying to remove 1 electron from p5. Which one you need more energy? Obviously the one that is more stable. So this one need more energy to remove because they're stable. So you need more energy to actually destabilize them, to remove it. So something more stable, you need more energy to disturb it, to change it. So therefore, this will have higher ionization energy for p6. So that's why we need to know which arrangement, which configuration is more stable. Then only we can deduce the ionization energy. So this is the third learning outcome. Still remember to evaluate the ionization energy of the electron configurations. So that's how we evaluate them. Okay, so next one is noble gas core. Now this is actually to facilitate your writing of configurations or to make your life simple. How to do that is something like that. Let's say I have 23 electrons like just now. You're going to write 1s2, 2s2, 2p6, and then 3s2, and then 3p6, and then 4s2 because I know I'm going to put in 3p. I leave a blank here, and then 3d3. Okay, 23. So this is the right formula. Now instead of writing a long configuration like that, they give a shortcut. You can use noble gas group 18 as a core. How to do that? Usually we will use argon because that will make a difference. Argon, what is the configuration for argon, guys? 18, right? And what's the arrangement of argon then? 1s2, 2s2, 2p6, 3s2, 3p6. There you go. So this is the electron configurations of argon, which compose of 18 electrons. Isn't it the same as this? Right? Part of it is the same because that's the fact. Because you arrange that 18 electron, the part of the configuration, part of the arrangement, it will be similar to argon. So instead of writing 1s2, 2s2 until 3p6, you can change this thing into square bracket argon. Then others will know these represent 1s2, 2s2, 2p6, 3s2, and 3p6. That represent everything, and then you just need to put in 3d3, 4s2. So compare way number 1 and way number 2. Which one is much easier? Obviously this. Easier. But of course, in exam, would I penalize if you write it in a long way like that? No. I mean, both are correct. So you can choose one, up to you. That's your choice. All right, I'm just showing you that, okay, there are some simple way to write the configurations rather than write out the full configurations. You can use group 18, noble gas. Argon is the most commonly used noble gas core. We call that as core because that represents a certain fixed configurations arrangement. Okay. Now, in the periodic table, we learn about group numbers, we learn about periodic numbers, period 1 to 3, group 1 to 3, right? So in this case, once we learn about SPDF, we can actually divide them into different block. We call that as S block, which is group 1 and 2. D block, which is the transition. P block, which is the non-metal. And F block, which is the rare elements. We actually put them into this. And how can we categorize them and how? So S block meaning that group 1 and 2, no matter how many electrons it has, whatever elements in it, right, they will always end at S orbital. It can be 1s, 2s, 3s, 4s, 5s, 6s, whatever. So the last orbital, it's always S. Therefore, they put it as S block. Now, P block meaning that the configurations, right, they always end at P orbital. It can be 2p, 3p, 4p, 5p, regardless. You can take one element and Google search, or you write it out on your own. They always stop at a p orbital. Therefore, all the elements here known as p block. Same for D and same for F. So this is how we differentiate them in block. All right. And factors, this is the last section, guys. Factors affecting ionization energies. So we learned that in SEM 1, the distance, the core charge, the shooting effect, all these things we learned, right? And how these things actually affect the ionization energy. The last one, this is the new thing that we need to know, which I have explained to you. Half-filled or full-filled p and d orbitals give extra stability. So we have to take into considerations when we are removing electrons, because when you're removing from a half-filled or full-filled p or d orbitals, you need more energy because they're extra stable. So this is what you need to consider other than what we learned, the core charge, the shooting effect. Basically, the distance between nucleus and electrons same as the shooting effect. When the distance is further, the higher the shooting effect because you have more electrons in between. So that's how it works, right? So I give an example how, right? This trend down the group is the same as what we learned last time. Trend across a period due to core charge increase, shooting effect stay constant, everything the same. But then look at this. I'll take the first case, this thing first. Okay, let's look at this. Now, between beryllium and boron, which one having a higher or lower ionization energy? Look at that. First ionization energy of boron is lower than beryllium. Basically, beryllium is having higher IE. And why? Because, let's say, I'm going to remove the first electron from both beryllium and boron. So beryllium, I take out 1. Boron, I take out 1. Where would I take it out from? The blue orbitals. This is the outer orbitals. This is the outer orbitals. We're going to take out from here. We always take out electron from the outer shell, from the outer orbital. In this case, beryllium is 2s. Boron is 2p. Now, obviously, this is about shooting effect. Which one experience a greater shooting effect based on the configuration? Look, how to know? Beryllium, how many internal electrons? 2 electrons internally. We don't count the 2s because we were going to remove from there, right? And how many internal electrons for boron? 4 internal electrons. So which one, 2 or 4, giving you greater repulsions? Or which one giving you greater internal repulsions or shooting effect? Because that is shooting effect, right? The repulsions between electrons. Obviously, this one giving you higher shooting effect because you have 4 internal electrons. When give you higher shooting effect, that means boron will have lower ionization energy because Higher shielding effect means easier because they keep repelling away from the nucleus, and it's much easier for you to take it away because they are not strongly attracted by the nucleus. They are getting further and further away from the nucleus. Therefore, it's much easier for you to remove it. So the one with the high shielding effect is the one with the lower ionization energy. That's about it. Okay, so I can show you another example before we end the video. So look at that. Let's look at the second case, right? Phosphorus and sulfur. Oh, sorry, the red color will actually interfere the things. Let me redraw it again. So let's look at phosphorus and sulfur. All right. Now, the outer orbital is 3p and 3p. Oops, both are the same at the outer orbitals. So I'm going to remove electron from the same orbitals now. Does that mean phosphorus and sulfur will have the same first ionization energy because they're from the same orbital? So technically I will need the same amount of energy to remove them, right? Because I'm removing it from the same orbital. Answer is definitely no, because here it states that first ionization energy of sulfur is actually lower than phosphorus. Phosphorus is higher. Why? Why? Because look at that. See that? Half filled, full filled, right? Extra stable. Come back. So I have 3p3 and 3p4. Isn't it 3p3 is half filled? P3, 1, 2, 3. Half of the total, half filled, right? But PP4 is not half filled. It's like 1, 2, 3, 4. It's not half filled nor fulfilled. No, not either one of them. It's not fulfilled, it's not half filled. So this is extra stable. And that is the reason why when you remove electron from 3p3, it's slightly harder than 3p4, even though they are the same. So phosphorus will have higher ionization energy. That's the reason why. And in terms of shielding effect, you may ask, would the shielding effect causes an effect? Would that have an effect on it? No. Look at that. Phosphorus. How many internal electrons other than the outer? So 2, 2, 4, 6, 10, 12. Phosphorus is 12 electron internal. And same, sulfur is also 12 electrons. So what can I say from here? Shielding effect stays constant. Exactly constant, because both are having the same number of electrons. But then, due to the half-filled and full-filled, they have different ionization energy. So I hope you got that, but you can try the next two example here and let me know if you need help in the tutorial, right? So I'm going to stop here and enjoy watching. I'll see you again. Thanks.